So the next speaker is Vanya Wagner from University of Zagreb of beautiful Croatia, and she is interested mainly in stochastic processes and non-local operator potentials and relation to Markov processes. But today she will speak about semilinear equations for non-local operators beyond the fractional Laplacian. Please, Vanya.
Okay, sorry. So I'll just use this opportunity to thank the organizers for organizing this wonderful workshop and this program in these challenging times. I'm very glad to be here. So yeah. Thank you. Like this? Test, test. Okay, thank you. So today I will be talking about semilinear equations for non-local operators, basically generalizations of elliptic non-local semilinear problems where generalizations stem from the non-locality in space, so to the operators, and also to the domains on which the problem is posed. So this is the joint work with Ivan Biocic, who will also present his part of the of some generalizations on Friday, and Zoran Vondracek from Zagreb. Okay, to start with, let me just say a bit about the type of problem that we are looking into. So we are working in a multi-dimensional space, looking at general bounded open sets. So D will be just some regular bounded open set. We consider basically uniqueness and existence of solutions to non-local analogs of the Dirichlet problem. This is a Dirichlet semilinear problem. So the semilinearity is given by this function f. We have so this effect from space and also from the x component and from the function itself. And when I say the Dirichlet problem, I mean by prescribing some complement, and we will see additional boundary datum for the problem. So when we talk about the Dirichlet non-local problems, then we talk about prescribing some data on the complement, but we'll see that in order to say something about the existence and the types of the solutions, we need to prescribe certain boundary datum. Okay, so this operator L here is just a generalization of, you can think about it as a generalization of a fractional Laplacian, in the sense that it is a second order operator which is basically obtained through subordination by some complete Bernstein function. So we take the Laplacian and then we subordinate it with a complete Bernstein function psi. These results will be mostly concentrated on some, we will see nice generalizations of the power function, meaning that we will need some additional scaling conditions on this complete Bernstein function. So basically our operator L is the subordinate Laplacian. The basic example always that we keep in mind is the fractional Laplacian. This is basically the Riesz type fractional Laplacian given through this principal value integral. Then we look at the nonlinearity or the semilinearity here, function f. this is some nonlinear function to keep in mind. Maybe it's best to just ignore the space dependency and think about the power function with a power greater than 1. In order to prescribe the datum, we can of course prescribe some function conditions on the complement and the boundary. Here, these conditions are given in a much more general setting, where the function on the complement can actually be thought of as a measure on the complement. So here, the complement value is given through a signed measure on the complement, and the boundary condition is given through this bounded measure on the boundary, basically through this, what we call some type of boundary trace operator. We will see how we define this boundary trace operator in general open sets, and show that this is precisely what we want from an analog in the local setting in smooth domains. So we will also look at let's say, the meaning of this boundary trace operator in smooth sets, and see that this is the generalization from the local setting. Okay, so in order to present our work, I will just say a bit about this setting and the introduction of these results. So the first, at least to me, known result in the terms of prescribing the semilinear problem in the non-local setting through the complement and the boundary datum in relatively general open sets, these are C11 domains, is a work by Nicola-Betangelo for the fractional Laplacian. Then thinking about this boundary operator that we mentioned in C11 domains, we will show that this boundary operator is precisely something of a condition on the function u, or the condition on the explosion rate on the function u near the boundary. This explosion rate in the fractional Laplacian case is precisely given by the distance to the boundary to the power alpha half minus 1, okay, which is the explosion rate of harmonic functions for the fractional Laplacian. Then in the paper by Bogdan Jaroks and Kania from 2020, moving from the C11 domains to more general regular domains, we need, or the idea was to generalize these type of boundary conditions in order to accommodate these more general sets. And here we see the first idea of, or the definition of the corresponding boundary operator WD. This work has also been treated only the alpha stable case. And then in the joint work by with Ivan Biocic and Zoran Vondracek, we extend these types of problems to more general non-localities and discuss for general open sets. Okay, so just to recall the local setting and the semilinear problems for the classical Laplacian. So we can prescribe these types of semilinear problems in some bounded C2 domains. And here the function f is usually taken to be continuous and non-increasing. This non-increasing condition generally gives us uniqueness of solution. Then we have some integrability conditions of the function f in space. This is basically integrability in this weighted space with this is the weight distance to the boundary of the set. And the usual condition is that if a function f is a power function, then we look at the superlinear case, or we impose some type of conditions. Okay, so if we talk about the local setting, then we can prescribe two types of boundary conditions, either by prescribing some function on the boundary, or more general, just prescribing a measure on the boundary, or looking at the solutions which blow up at the boundary, so which have a certain blow up. And we say basically what we look for weak solutions to these type of problems. So we say that the function u, which is integrable on D, is a weak solution to this type of semilinear problem, where here we have the boundary datum prescribed by a measure. If this function u satisfies this certain integrability condition, and the following holds. So the integral over D of the function u integrated over the Laplacian of some test function from the C20 space on D is equal to the function f evaluated at u integrated over phi on D, and we have here this is the outer normal derivative of the function phi with respect to the normal on the boundary, integrated over the boundary condition mu. So what we want to give a non-local analog of this type of solution and this type of problem, now not only in smooth domains, but in more general domains. Okay, so these type of solutions that have finite boundary conditions are called moderate solutions. So they're called moderate because they are harmonically dominated by some harmonic function for the Laplacian. And the idea of this talk is to give the analog of precisely these moderate solutions to non-local problems. So the non-moderate type would be with the explosion on the boundary, and this is the case that we don't consider at this moment within this talk. Okay, so this boundary datum, this function mu, is basically the M trace of the function which is locally in this Sobolev space, and this M trace is given through this weak convergence. So basically, we know that these functions have locally some traces. So if we take some C2 exhaustion of our set D, and we look at the trace of our function u on the boundary of these exhaustion spaces, then this integral converges, that is the integral with respect to some continuous function up to the boundary, converges precisely to the integral with respect to the boundary measure. So this is this M trace measure of the function u. So what we want to do, we want to generalize also or show these generalizations of these M traces. Okay, so when talking about the extension of the semilinear Dirichlet problem, we basically need to give some type of generalization of this M trace. This will be given through the boundary operator WD. Keep in mind that this generalization holds for general domains, not only smooth domains. And then we want to comment on the moderate solutions. These will be precisely the ones that can blow up at the boundary. So in the local setting, we have the possibility of blow up at the boundary, but the rate of blow up is controlled by the rate of blow up of harmonic functions. In our general non-local setting, this is given through this characteristic exponent or Laplace exponent phi of the subordinator, or if you think just about the fractional case, this is precisely the order distance to the boundary alpha to the power alpha half minus 1. Okay, so introducing the non-local setting, we have a complete Bernstein function with zero drift. This is the function given through this integral form here with respect to the this completely monotone function in U. So we've recalled the definition of completely monotone functions in the second talk today. And we also impose this integrability condition on the function U. Now, given this complete Bernstein function, what we do, we look at a stochastic process whose Fourier transform of the transition density is defined or determined precisely through this function phi. So it's equal to e to the power minus t phi of psi squared So this is precisely the subordinate Brownian motion. That is a Levy process which is obtained through subordination of the Brownian motion via this subordinator. And its Levy measure, J, is given through this integral form. So it is completely determined by this function in U or this Levy exponent phi. Okay, our generator will now be the non-local operator given as the principal value integral through this jumping density, this Levy density J here. Okay, so here, if we just put the classical fractional density, we obtain the fractional Laplacian. Okay. And also one nice way to think about the connection of the operator L and this Laplace exponent is precisely through this Fourier symbol of this operator. Okay. In our setting, what we require is a certain scaling condition. So this is an analog of the real true scaling that is exhibited by the alpha stable subordinator. But note that we here allow that the scaling is basically between two different power functions. So the ratio of phi of t and phi of s is between two some power functions of t over s. Let's just think about it in this sense. In the fractional case, A1 is equal to A2 and delta 1 is equal to delta 2 equal to alpha over half. So this is the standard example, but to move from the exact scaling, we can also consider this Bessel-Rees process given through the following Laplace exponent. Here we don't have the exact value or the exact values for the jumping density, but we have this upper and lower bound on the density in terms of the parameters alpha and gamma. Okay, so in order to present the notion in which we define the solution, I will just recall or introduce some potential theoretical notions such as the green function, Poisson kernel, and the Martin kernel. So if we take a D-bounded open set, and we can denote by tau D the first exit time of our Levy process outside of the set D, and then consider the killed process. This is precisely the process which is equal to our original process up to time tau D. And then upon exiting the set, we just kill it, send it to some additional symmetry state. Then we can look at the, this is the semigroup of this killed process and the corresponding transition density, which I will denote by PdTxy. So this transition density can be obtained using the strong Markov property directly from the transition density of the original process. Now we define the green function of the killed process at D. So basically we define this green potential of function f as the integral from 0 to infinity of the semigroup on the function f dt. So this is evaluated at point x. This can also be written through this integral through the kernel, which we denote gdxy, and this kernel is called the green function of the killed process. If you just put an indicator function of some Borel set instead of f, you basically get the expected time that the process spends inside that set before exiting the set D. Then we define the Poisson kernel of the process on D by this integral formula. So for a function, for a point x in D and point z in that D complement, we define the Poisson kernel as the integral over D of the green function, so integrating over the second variable, and times the jumping density from the point y to the point z. So basically, if we look at this, this is basically the density of the exit position of the process when it exits the set D, if it exits the set D away from the boundary. So you can think about it as the transition density, or the not the transition density, but the probability distribution of this exit point if the process started from the point X in D. Okay, and now we denote by D by this partial MD. This will be the set of all accessible points from D. I will not say too much about this set within this talk, but these will be just the points on the boundary for which the Poisson kernel is equal to infinity. So when this limit when z approaches the boundary, then this is precisely infinity. If it's infinity for one x, then it's equal to infinity for all x. And now we define the Martin kernel precisely as the limit of the ratio of the green function of the point in the points x, y, and the green function at the point x0, y, where x0 is some fixed point that we fix and define the Martin kernel with respect to it. So the Martin kernel is defined for X in D and Z in on the boundary. So I am not, again, mentioning too much here, but this Martin kernel and the corresponding Martin potential are very closely related to the characterization of harmonic functions for these operators. Basically, every harmonic function can be prescribed or can be defined as a Martin potential of some measure. Okay, now using these notions, we define this boundary operator. So how do we define the boundary operator? We take a series of measures which are defined on the whole set U, and we push these measures. So we take some exhaustion of our set D, and then these are these sets U, and then we push these U to cover the whole D. Basically, we get a limit, which is a weak limit of these measures, nu U. So for a fixed function U, we prescribe a measure on U, which then in the weak limit converges to a function, to a measure, which is a measure on D. This is a measure on D, but basically the support of this measure is precisely on the boundary. So it is a bit maybe hard to see what is happening here, but think about it in this way. You are prescribing to the function U a measure such that the measure of this set A is precisely the integral of the function U over the all exit points of the process, starting at x0 here, and then spending all the time, so spending some time at the set A, okay, before exiting the set U, and then you integrate over the jumps from this point Z outside of the set U. So if we take U to be here, this would be precisely the Poisson potential of the function U over the set U. Okay. Now it's a bit, so this is done in general domains, so this is maybe a bit hard to see, but what is important is that precisely the boundary trace of this Martin potential of some boundary measure mu is exactly mu, while the boundary operator completely misses the Poisson potential and the green potential. And this boundary measure that we get through the operator WD is precisely what we call the analog of the M-trace function. M-trace measure, sorry. Okay, so now that we have all the three components, we basically look at what we call weak dual solutions to the original semilinear problem. So these are the functions U, which are integrable on D, which satisfies the following equality for almost every X in D. So basically, the function U can be represented as the green potential of the function F evaluated at U, the Poisson potential of the complement measure, and the Martin potential of the boundary measure. And then we have, of course, the super solution and the subsolution. So just to give an idea of how this generalizes the classical setting, we define the generalized normal derivative. So the generalized normal derivative is basically nothing else but this limit of the function over this function of the distance to the boundary. This function V, this is a renewal function of the ladder height process of the corresponding one-dimensional subordinate Brownian motion. But think about it just as a function which is given through our Laplace exponent phi. In the classical fractional setting, this is precisely distance to the boundary to the power alpha over half. So this would what would be the fractional normal derivative, and we here define the generalized normal derivative. So this generalized normal derivative can be given through as integral over this kernel KD, which we can call modified Martin kernel, because it's basically the Martin kernel that we've seen before, just divided by some, let's say, Z-dependent factor. So it is almost the Martin kernel that we saw before. Okay, so now moving to the C11 setting and the generalization of the classical semilinear problem. So if we evaluate a function phi, which is given as the green potential of some smooth function, or if we evaluate the operator L of the, up to this function phi, then we know that it is equal to psi on D, and we have this the integral with respect to the Poisson kernel in the complement. So basically, our function U is a solution if it satisfies this equality. Writing down in terms of this, in terms of the evaluation of phi over L, we basically get this form, or analogously this form here. If we denote this corrected measure mu by mu tilde, what we get precisely the analog of the local setting. Here on the left-hand side, we have the integral over D of our solution with respect to minus L, so our operator to phi. This is precisely what we have on the left-hand side. Then we have the integral of the semilinearity evaluated at U with respect to phi. This is the same thing in the local setting. Then we have here what is the generalized normal derivative of the function phi. This is the inner, this is the outer one. That's why we have a minus here, what we see here. And again, we have this complement value, which is not seen in the local setting. Okay, so just to present quickly some results. So this is the setting that we are working on. We are looking at a semilinear function. We will always have different conditions. So we take some, this function this function f can be split up into the space-dependent part and the function-dependent part. And if we assume non-increasing, then we get some type of uniqueness results. So let me just quickly tell you what the results are. So it's easier if we think about this in the terms of the powers. So basically, one can generalize completely in the classical results with where f is the power function in terms of the fractional Laplacian with respect, so in terms of this function v or the Laplace exponent phi, and get the existence of the solutions for very general semilinearities. These conditions given out, so this is a condition written for smooth domains. Moving from smooth domains to more general domains, we can rewrite these conditions in terms of the green potentials of these functions that we see here. But this is, of course, something that gives us a more general result. For smooth domains, it is much easier to think about 7. So these are some sufficient conditions in order to have a harmonically dominated solution. And you see that this here exponent p is not optimal. This can be extended by looking at non-positive functions f on the right-hand side. In this sense, we can extend the results to the full fractional result that that is very well known so far. And this condition is given precisely through the integral condition 8, which is weaker than the integral condition that we've seen previously, 7. If you want to state this in more general terms for more general domains, then you get some integrability condition of what we see here. This is the function f in some sense, and the green potential of function 1. So what I would like for you to take out of this small presentation is by posing the solution or the problem in terms of the potential theoretical notions, one can extend these general fractional semilinear results not only to more general non-local operators, but to very general domains. And these conditions are then prescribed in terms precisely of these integral conditions through the green potential. Okay, and here are some references that you can take a look. So Nicola Betangelo's work on the smooth domains and the fractional Laplacians. Then here we have 2 generalizations for more general non-local operators. And in the papers by Bogdan Yarokskania, Bogdan Gluchitsky, and Kwasniewski, we can see the construction of this boundary operator WD, which allows us to move from smooth sets to more general domains. And this last one is just a standard textbook on nonlinear second-order elliptic equations for local operators. Okay. Thank you.
Okay, thank you very much, Vanya, for an interesting, most of practical talk. And any questions or comments? Again, from those who are not here and participating in online, please unmute yourself, introduce and ask question again.